Welcome to our video on new bounds for kernel sums via fast spherical embeddings. Let me start with an overview of the main theorems. The first one is a fast Gaussian kernel density estimation algorithm, which is faster than the previous ones in a certain regime of parameters. And the second one is a fast spherical embedding theorem, which maps your points onto a sphere in a way that approximately preserves their distances. They may seem unrelated, but they are actually very related. The first theorem is a consequence of the second theorem, as we are going to see. The main problem we focus on is Gaussian kernel density estimation. The input is endpoints in R to the D, and our goal is to take a query Y and return an estimate of its KDE, which is the average of its Gaussian kernels with each one of the points in X. This means we put a Gaussian centered at each point in X, and our goal is to estimate the density of Y in this mixture of Gaussians, and we want to do this up to error plus minus epsilon with high probability as fast as we can. This is a classical problem with many classical methods in the literature. This is a list. The one I want to call out is the last one, fast food, from ICML 13, which has running time d plus delta squared over epsilon squared. There is a new parameter here, delta, which is an upper bound on the diameter of the point set, so they are assumed to lie in a bounded region. And now I can get to our new bound, which also has this delta dependence in a different way. It's d plus epsilon delta squared plus 1 over epsilon cubed. So neither of the bounds on this list is better than the other ones across the board. It depends on the regime of parameters where you're operating. So if we focus for a second on the high dimensional case, where it's always better to be d plus something over d times something or more, then on the top you can see the interplay between the methods before our work and on the bottom with our work. So there is a large regime of parameters where our method is currently the best. And still, this is a long list of bounds. It raises the question, what is the best bound you could get? I don't know the answer. One can hypothesize it's maybe d plus 1 over epsilon squared, but this is an open question. Our plan of action is going to be to find the fast way to reduce the diameter, and then we can apply fast food as a black box, because in a sense, its only weakness is the dependence on the diameter. And the main tools we are going to use for that are dimension reduction, random Fourier features, and randomized Hadamard transforms. So let's start with the blueprint for KDE. This is a framework that all of the bounds from the previous slide adhere to. They choose a feature map, F, such that the inner product between the feature vectors of every pair X and Y is approximately equal to their Gaussian kernel. If we have that, we can pre-compute the average feature vector of the dataset, and when we get a query, we can return the inner product of its feature vector with the pre-computed vector. It's not difficult to see that this is approximately equal to the KDE. And one classical way to get these features is random Fourier features, which satisfy this property in expectation. So to get plus minus epsilon approximation, you need time d over epsilon squared. Now, to speed this up, let's think about dimension reduction. If the dimension is high, maybe it's a good idea to reduce it. The Euclidean dimension reduction theorem tells us that we can map our points to a lower dimension in a way that preserves all the distances. However, this takes time d over epsilon squared, which is not faster than random Fourier features. Fortunately, there is a faster version of the theorem using randomized Hadamard transforms, which runs in time d plus 1 over epsilon squared. However, it doesn't reduce the diameter, which is what we want. Of course it doesn't. It has to preserve all the distances, including the diameter. But then there's also this spherical version of the same theorem by Bartalek and Schulman. So this theorem maps your points to a sphere in a way that strongly preserves only the small distances and only weakly preserves the larger distances. This is enough for KDE. Because of the fast decay of the Gaussian kernel, the larger distances are kind of negligible anyway, so it's enough to preserve them only in a weak sense. So this is great, and it also reduces the diameter because it maps points onto a sphere which has bounded diameter. Unfortunately, the running time is again d over epsilon squared, not better than random Fourier features. This time there is no, or there was no prior to our work, a faster version of this theorem, and this is what we fix. So this is our fast spherical embedding theorem. Just to go over it quickly, the non-expansion and non-contraction properties from the first two bullets strongly preserve the small distances, and the non-collapse property from the third bullet weakly preserves the larger distances. And to compare it to the theorem of Bartalek and Schulman, their non-collapse property holds in a larger regime because it doesn't have this delta parameter that we have. But their embedding time was d over epsilon squared, which is not helpful for KDE, while ours is. And as promised, the way we apply it is we use it to reduce the diameter of the points, then we apply fast food. The final features that we get have the form of 4 consecutive randomized Hadamard transforms. I didn't have time to tell you what they are in this video, but the form of the features is pretty simple in the end. And just to quickly conclude, these are the main results. There are extensions to other kernels and to other settings like differential privacy. There are interesting open questions that come out of it, and this is it. Thank you for watching.